So let's say we've got a large charged object over here and a small charged object over here. What's going to happen is that these are both applying forces on each other. Object A repels object B repels object A. Same force, opposite directions, Newton's third law. But there are many cases in which we don't really care about the forces acting on one of the objects. Maybe this object is so massive that it hardly moves at all. Maybe it's rooted in place by other forces. Maybe it's attached to some sort of framework. Maybe it's moving, but we don't care. We're going to call that the source object, or source charge. And this other object, we really care about the forces acting on that. We're going to call that the test charge, or test object. So even though they're both applying forces to each other, we're going to treat it as if the source charge is creating some sort of effect that applies a force to the test object. Now let's say we measure the force on that test object, and we find that it is a force of 30 newtons. 6 coulomb charge experiences a 30 Newton force. And let's say we put a different charge there. And I don't care about the forces these charges apply on each other. Let's say we remove that 6 coulomb charge and put a 12 coulomb charge in the same spot. A 12 coulomb charge in the exact same situation. How much force should that experience? Well, it's twice as much charge, so we should expect twice as much force. 60 newtons. Since this charge of 12 coulombs could be thought of as just 2 copies of the 6 coulomb charge bolted together, so they experience 2 times as much force. Or suppose we had a 2 coulomb charge. That's 1/3 as much charge as the original, so we should expect 1/3 as much force. Or alternatively, what if we used a negative charge in that same spot? Maybe a -3 coulomb charge. That's half as much charge as the original, so we should expect half as much force. But what does this negative sign mean? That's going to get attracted, so it experiences a force in the opposite direction. 15 newtons to the left. So all these particles are experiencing different forces. And why is that? Why do these forces behave differently? Different forces because different charges. And we've been assuming all along that these are proportional. That twice as much charge means twice as much force. 1/3 as much charge means 1/3 as much force. So we can write this out as a proportionality. We've been assuming that force is proportional to charge of the test object. And anytime we've got a proportionality, we can write that as an equation. When we say F is proportional to Q, we mean F equals not just Q, but Q times something. Force equals charge times something. So there's got to be some quantity we can multiply by the charge of the test object to figure out the force acting on the test object. And we call that quantity, that multiplier, we call that E, the electric field. And why does that have to be a vector? Force is a vector, right? It's got a direction associated with it, but charge is a scalar. If you're going to multiply a charge by something and get a vector, that something has to be a vector. The direction has to come from somewhere. So this is one way we can define electric field. Electric field can be thought of as the vector multiplier you apply to the charge to figure out the force that acts on that charged object. And anytime we figure out that we have to define some new variable, it's a good idea to look at the units of measurement. We've got force measured in newtons, charge measured in coulombs. So electric field better be measured in newtons per coulomb. And you'd think that at some point in the last 200 years, somebody would have named newtons per coulomb after some dead physicist, but As far as I know, it hasn't happened yet, so it's still just newtons per coulomb. We can get more information about E and what it means by solving for it. If we isolate E algebraically, by just dividing both sides by charge, we get E equals F over Q. And a very useful way to think of electric field is it's the force that would be felt by a charged particle, but with the charge divided out of it, ratio of F over Q. And a very useful way of thinking of ratios like this, the easiest number to divide by is 1, so just imagine that you're dividing by 1 coulomb. The electric field could be thought of as the force that would be experienced by a 1 coulomb charge. And given this definition of the electric field, let's see if we can calculate what the electric field is in this scenario. Because in all of these situations, we've got a force and a charge, so let's try dividing. Electric field equals force over charge. So for instance, in the first one, that'd be 30 newtons over 6 coulombs. 30 newtons over 6 coulombs. So that's going to be 30 over 6, 5 newtons per coulomb. So 30 newtons divided by 6 coulombs tells us that this charged particle is noticing a 5 newtons per coulomb electric field. But if we try for the next one, again dividing force by charge, 60 newtons divided by 12 coulombs is also 5 newtons per coulomb. 10 newtons divided by 2 coulombs is also 5 newtons per coulomb. And since these are all a force to the right divided by a positive scalar, that has a direction also. The electric field is 5 newtons per coulomb to the right. Now we come to this negative charge. It's experiencing 15 newtons of force to the left, but a vector to the left divided by a negative charge becomes a vector to the right. So the result, electric field, is still 5 newtons per coulomb to the right. So all of these charges, even though there are different charges experiencing different forces, the electric field is the same, because the electric field is the ratio of force over charge. And this means that the electric field doesn't depend at all on what test charge we use. It only depends on the location in space. So the electric field is a property of the location in space, whether there's a test object there or not. And that's why we can call it a field in the first place, a property of that location in space. Of course, this also depends on the source charge, which we haven't been talking about. If the source charge is larger, all these forces increase. So a larger force divided by the same test charge is a stronger electric field. So electric field strength depends on the source charge and also how far you are from it. If we move all these test objects closer, they experience a stronger force. Stronger force divided by same test charge leads to a larger electric field. So electric field gets closer if you get closer to it gets larger if you get closer to the source charge, gets weaker if you get further from it. And as I said, you can think of the electric field as the force that would be felt by a 1 coulomb charge, specifically a small positive charge. So if you wonder which direction should the electric field point, ask yourself, if I put a small positive charge here, which direction would the force point? And we should expect the positive small charge to be pushed away from the positive source charge. So the electric field is going to be pointing away in all directions. Or if it was a negative source charge, pointing inwards from all directions. So that's the core idea of electric field. You could think of the electric field as the multiplier to apply to a test charge to find the force that acts on that test charge. Or you could think of the electric field as the ratio of how much force the test object experiences over its own test charge. That's the core idea.